Alright, so the previous video was about pressure in general. This video is about pressure underneath the liquid surface. So this is a little bit different. We're still talking about force being applied over an area, but things are a bit different when we're talking about underneath a liquid. So this would be like actually atmospheric pressure counts, even though gas, the atmosphere is not actually a liquid. It's a fluid still. It still counts as a fluid. Gases and liquids both are similar to each other in their properties, so we can talk about the same sort of pressure of the atmosphere, and don't worry about that right now. The main thing we're focusing on here is underneath actually a liquid. Okay, so if you go scuba diving, for example, then we'd be talking about the pressure you feel as a result of being underneath the water, the surface of the water. Okay, and it turns out there are several factors involved when you're trying to calculate or talk about the pressure that's underneath the liquid. So the first one, I suppose I'm going to relate this back to pressure in general. Alright, so what you can see here is this is an aquarium. I guess this is an aquarium in Georgia where they have a whale shark in captivity. Georgia in the US, not in Russia. And then you've got a bunch of people standing here watching, right? So clearly, these people are not underwater. They're in front of a large pane of glass. Interesting fun fact for you. You notice that pane of glass is, compared to the size of the people, that's quite large. I don't even really want to think about how much pressure there is, how much force is being exerted on this pane of glass right now. And I really hope that the people who designed this pane of glass knew what they were doing, because that is a huge amount of force on that glass. So anyway, we'll talk more about that later, but I think you would be shocked at the sheer magnitude of how much force and pressure there is pressing against this glass, and these people aren't even thinking twice about it. Alright. Another example. Here we've got a scuba diver. I don't know if any of you have been scuba diving, but quite possibly you have. So you may know that as you scuba dive, the pressure on your body increases as you go deeper under the water. So the further under the surface of the water you go, the more pressure there is on your body. You're able to use the scuba gear in order to balance that out and keep breath in your lungs and all that kind of stuff, which is really cool. But basically, the pressure of the water exerted on your body increases the further down you go, because basically you can think of there being all this weight of water up above you that's pressing on you, right? And actually, it presses in equally from all sides, right? So the pressure comes in, all the pressure at that depth comes in from all angles, okay? So you're basically being pressed on equally all over the place. It's not like it's just pushing on the top of you and the bottom of you is not being pushed on. All of you is being pushed on. Alright? Cool. So basically the bottom line here, pressure increases as the depth below the surface increases. So if we look back at this picture one more time, the pressure down here at the bottom of the tank is greater than the pressure up here at the top. Okay, so if we put this in the form of an equation, we're going to get this guy right here. Pressure is equal to the density. It's this little rho. That's Greek. That's the Greek symbol rho. All right, and that's what we use to represent pressure. Sorry, that's what we use to represent density, not pressure. That's what we use to represent density. All right, so that's density of the liquid. Okay? So we've got P is pressure, rho is density, G is the acceleration due to gravity, and then H is the depth below the surface. So basically, just to summarize that, here we go. It's all written out here for you. All right? So that's the equation that we use for calculating the pressure underneath of a liquid surface. All right? Now, what kind of, it's not always going to be water. Just letting you guys know that right now. Any liquid, you can use this to calculate the pressure underneath any liquid. So we might talk about water, right? But we also might talk about mercury. And we will, in fact, talk about liquid mercury, which is what is right there in this beaker. You can tell it's mercury because it's silvery looking, it's liquid at room temperature, and what do you see there floating on it? That's a coin. That is a coin made out of metal that's floating on the mercury. Mercury is quite dense, and it is liquid at room temperature, which makes it really interesting to work with. It's also toxic, so we won't be doing this in lab, where you get to pour some mercury in a cup and stick something on it. We're not going to do that. It's toxic. We'd get in trouble. So you guys don't get to handle liquid mercury. Sorry. All right. So basically, relevant factors for pressure under a liquid surface are the depth under the surface of the liquid, how deep you are below the top of the liquid, and then the density of the liquid. What's it made out of? All right. So let's just look really quick at a couple of sample problems. Okay, so we've got here 4 different glass containers, and they all have liquid in them. It's the same liquid in each one. They all contain just water. So then the question is, which tank has the greatest pressure at the base due to the liquid? All right, so do you remember your equation P for pressure? P equals rho times G times H. So we've got, that is the equation. Do you guys see area or volume anywhere in there? You don't, because the only thing that matters is how deep you are under the surface. All right, so given that fact, the only thing that matters is how deep you are, then which one has the greatest pressure on the base of the container? That would be this one, A, because it is the deepest, and that's all that matters. Just to take a side note, if you were to take a little pool, say a 10-foot by 10-foot pool, and say it's, well, let's go with metric system. It's 3 meters by 3 meters, and the depth, we'll just say it's 3 meters deep, so it's a cube, the shape of the pool. Maybe it's a pool at a hotel or something that's by the ocean. And let's just say that they put salt water in this pool because it's convenient and there's lots of ocean nearby, so they just pump some salt water up into the pool. Okay, so there's a saltwater swimming pool, and you decide to dive to the bottom for whatever reason. So you're 3 meters down under the surface of the salt water. Now, so remember, the salt water, it's like 3 meters by 3 meters on the surface of that salt water. And then let's go say you take a dive in the ocean down to 3 meters, right? So you've got this 3 meter by 3 meter pool, and you dive 3 meters down, and then you go into the ocean, which is, you know, thousands of kilometers by thousands of kilometers is the surface area of the ocean. So 3 meters down under the ocean, 3 meters down under the pool. Which one are you experiencing a greater pressure? And the answer is, the only thing that matters is depth, right? It doesn't matter if you're in the ocean or if you're in a pool. If you're at the same depth in the same kind of water, then you will be experiencing the same pressure, right? If surface area mattered as to how much pressure you experience, then you wouldn't even be able to dive in the ocean. It is so huge, you would be experiencing such a huge amount of pressure because of the surface area of the ocean. So the only thing that matters is the depth. All right, one more question here. This one deals with density. So we've got this student who fills 2 containers with water and 2 containers with oil. So this container and this container are the same kind of thing, and then this one and this one are the same kind of thing. So you've got water here, and you've got oil there and there. All right, and it tells you what the density is. Oil is 0.8 grams per cubic centimeter, and water is 1 gram per cubic centimeter. So which one is more dense? And the answer is water. Water is more dense. All right, so this is more dense. Here and here. So if you remember our formula for pressure under liquid surface, density is a factor, right? So there's going to be more pressure if there's more density. So basically, which one has the greatest pressure on the base? then you know that it's not going to be the oil because the water is more dense. So it's going to be one of the waters. And we know that the pressure under the surface is greater if the depth is greater. So which of these is deeper becomes the question. And the answer is A, is deeper. So A is the one that would have the greatest pressure at the base, inside the liquid. All right, cool. That's it for this. Hope that was helpful.